All right, greetings everybody. My name is Kevin Kawchek. I'm the founder CEO of Chemical Q Device here for event seminar 127. This is Thursday, March 21st, 2024 for Tensor Networks, PCA and PLS for high dimensional medical data sets. So basically what's shown here is this is reduced down to two dimensions with a technique called t-SNE. There's a variety of different high dimensional techniques to use to get it workable, but you can see this is something that's interpretable in 2Ds, and this was actually done on an Illumina sequencer in, I believe, 2023. Now, what's shown here is so the issue isn't the number of patients, it's the number of columns of data for a specific patient, and that these columns are referred to as P, with the number of patients being referred to as N. So you'll see here for these individual omics layers, epigenomics, transcriptomics, proteomics, metabolomics, lipidomics, and spatialomics, is it can have a lot of different dimensions per. So a lot of times it's not just returning a certain value for each of these. And on the computational scale of this, it's very challenging to do this on classical hardware. So a variety of techniques such as PCA and PLS, and I'll get to some other ones too, cover this as far as what can be broken down into smaller dimensions. So this is seen kind of like on the more computational side as a database, data mining, omics information. Is behind the scenes in all of this is, like I said, you'll have a specific number of patients. And it's not the patients that their issue, it's the number of dimensions per patient. And that's typically referred to as P, where the number of patients is N. So this is just a broad overview of what's going on, making things convenient to process. So how we see it, if you're a coder like myself, like we're always seeing just lots of data, spreadsheets. And what's shown here is you get the top three dimensions for a specific patient. Now, I'm just calling it patient 1, 2, 3. The prescription number might be a little bit redundant. So you see medication name is going to be a certain dimension like Advil, another prescription date, another dimension, and the third dimension prescription cost. So you could do all types of stuff with just not even that much hardware because it's only 3 dimensions. Now, the one shown below is a little bit more. So you see 5 dimensions, and this is referring to hospital ID, hospital name, hospital address, phone number, state, and zip code. So this is getting up there. So it's typically, between 4, 5, 6. If you want to do a lot of analysis and then go on to visualize data, it gets very challenging increasing the number of dimensions. So this study, the statistical analysis of high dimensional biomedical data, is very good to go over. It's not just high dimensional, it's all the steps leading up to processing high dimensional data. It does include PCA and PLS, which are, 2 of the more popular methods out there for high dimensional data processing. And you see this with, so they basically say with large number of variables, again, a variable would be like a P or a dimension as measurements across genome proteomics, and each of those have a lot of different dimensions. Now, as you hear the term big data does not always refer to big dimensions. And in this case, they say it's a combination of the two. So large N being the number of patients, and then large P being the number of dimensions of a measurement. It's the combination of those two that makes things challenging, mostly the P of the individual patient and what's happening with them processing their data. And you can see the number of variables is often in the range of tens of thousands or even millions. So there's a lot that goes behind the research that's reported in academia that gets truncated down to what you see in a 2D chart. A lot of data that is deemed either to be redundant or sometimes they'll combine. There's many techniques behind this in dealing with high dimensional data. Now, you heard me talk about this before, but singular value decomposition is the crux for principal component analysis, partial least squares, and also tensor networks. And it's one of those things, and I'll touch on it a little bit here, that's fundamental to understanding how to do high dimensional data with conventional hardware. So I'll go over SVD, and then I'll go over principal component analysis, and then I'll also go over partial least squares as well. Now, for the next part here, for tensor networks is basically saying like, this is the technique that's basically every, quantum supremacy experiment gets matched or beat, with tensor networks. And it could do quantum circuits, it could do regular complex data, high dimensional, low rank approximations. And these have been in previous lectures as well. And the myriad benefits that go with it. So if one paper is saying, hey, we're more using it to compress a model in a lot more explainable way, and we're getting the good specs, that's important. But you're also going to get good accuracy and loss and performance using traditional ways of compressing models, but using this quantum inspired technique, it has the inherent benefit of typically being a lot more explainable, controllable, and predictable, leading up to a prediction model. So the last thing is I ran a couple of these demos from iTensor and TenPy. They're two of the leaders with tensor network software. And it's basically, it's a good place to start. And I'll go over as far as which are being used more in literature. Now, starting off here, this is basically, if you're ever wondering if you're coming from different backgrounds, this is an effective approach to using a matrix, which gets broken down into these three parts. They're called U, S, and V. Now, the U and the V, which is actually transposed, those are on the two sides. Those do not get modified, but it's the S in the middle that does. And I'm sorry, it actually all three would. But you're looking at S in the middle to truncate these less variant values. So this 0.933 has high variance, or it's important. The next column is less important, and then the next column, this 0.2, is even less important. So what's shown here is basically truncating these two columns, which also truncates, the final measurement, and it produces this new matrix that's truncated, which is a controlled approximation of the original matrix that you're starting with. And this is all done in a very statistical way. It's not a random way of just removing data or discarding data. It's, like I said, with these three methods, they use it in different regards, but it's a way to get the dimensions down, to process, high dimensional data. In one paper, it said that corresponding to an infinite number of qubits or quantum bits, that it can now do that, and it's not limited by some exponential restriction, classical mathematics. So I would highly suggest to follow this channel. I'll have some of the additional information behind the author. He works at University of Washington, and it just completely opened up my mind more to SVD, this very fundamental. So you'll see U and you'll see S, and then this is the V here. It's basically, you're controlling the amount of approximation that you want, but it's also dictated by, say, this first column here is more important than the second one, is more important than the last one. So you go right to left and removing as much information of these other things that just don't correlate. So you need to think about this as it's very high dimensional data, and you can't just directly process in classical hardware this efficiently, effectively, if you want every single correlation. So there's different things beforehand, feature extraction, and you're just, you combine things, and it's a very common processes. But SVD is used in all three of these. And, this is shown also in PCA. So we see PCA, which is principal component analysis, which is thought to be more of a pre-processing machine learning technique as opposed to other things. And, it's still very, very, it's used very often, and there's quantum versions of it and that type of stuff. But basically, you're getting it into, like, the first component has the highest variance. The second one doesn't have as much. So when you see like these 2D charts, when you look at it, you would say, okay, in this direction, this has the highest variance, as opposed to other things like collinearity that aren't as desirable. Now, this is actually a Stanford lecture here, and it goes over some important points to define so basically, the first principal component is the normalized linear combination of the variables with the largest variance, okay? So that if you gain anything from this lecture, gain that is basically, the second component, less variance, the third component, less variance. So meaning people have done these with huge data sets and even 3D principal component analysis. So hence many correlated original variables, we can replace them with a small set of principal components. So when you see the next 2D, chart of your, principal components, you'll know which way to move to see which has the most impact there. And there's also dequantized versions of this. So this is actually taking a quantum algorithm, turning it into the quantum-inspired dequantized algorithm for the fastest speed up compared to these. Now, most dequantized algorithms aren't quite as fast as the original quantum algorithm, but if you're talking a substantial amount of speed up for the quantum algorithm, which can't be used today or whoever knows how long, you're getting some of that speed up in this dequantized algorithm, where the quantum algorithm no longer has an exponential speed up by mathematical proofs by Ewan Tang and others. There's at least 8 of these quantum machine learning algorithms that have been dequantized, and you can't use them with exponential speed up, with some speed up, but with you don't have exponential speed up into the future. So here's partial least squares. So this is the other one. So those that don't know how to use partial least squares, they try to use PCA, principal component analysis, and they say both methods are used to overcome the problem with collinearity in linear regression and in cases where we have more explanatory variables than observations. And the other thing here, it's also called latent structures, or the projection of latent structures, to reduce the number of explanatory variables. And this is the problem here, is collinearity, is that you get these huge error bars that's associated with PCA, and say if you could use partial least squares, then in that case that you should do that. And this is an example of systolic blood pressure as a function of the cholesterol and age. And then this one, you'll see that the new principal component is a function of cholesterol and age that you're dealing with now. And it's just that makes it more efficient to process. And we see this basically with partial least squares. The last one says, however, the problem with principal component regression, which is principal component analysis plus regression, is that it combines the variables without involving the dependent variable, which I believe in this case is the systolic blood pressure. So it's one of those things, like everybody loves principal component analysis, but there's certain cases to use partial least squares, and you will run into people and they say, well, we've just never had to use it, or perhaps they didn't know kind of like the inner workings of it with this. So partial least squares. So again, the partial least squares, principal component analysis, and tensor networks all use the same type of approximative methods to be able to work with high dimensional data, so that you can get to these huge problems. And again, it's not necessarily always the case if you're just discarding things. It's that you're looking at the correlations or variance. Like the more variance, the higher importance it has, then you would keep that one and discard other smaller ones. So here's another lecture too. And basically what you see here, direction of most variation. So there's it takes a while to go through all of these charts, but you typically see these on like a 2D plot, and in this case is actually 3D, but they're decomposed into latent structures. There's a lot of similarities between the three, between PCA, PLS, and then tensor networks. Now, I really like this demo. It's not medical, it's orange juice, but I really like this demo. It says 16 chemical and sensory characteristics graded by 96 consumers. So you see all of these dimensions here, okay? So the first couple I showed you were medical, smaller, maybe 3 or 5 or 10 dimensions. And now you see all of these columns applied to a single juice. So for this first one, or you could look at this like patients, if it's medical, that the specific product has this much glucose, fructose, saccharose, these are sugars, sweetening power, acidity, citric acid, those types of things. And, some of these things, are correlated. And here's the correlations here. So it says acidity and citric acid are correlated because it's an acid. Acidity and pH anti-correlated. Bitterness and acidity correlated. Glucose and fructose correlated. So some of these are kind of like, yeah, we kind of already know that, but it's a good exercise nonetheless, and seeing more dimensions with this. And this is basically how it shows up in this 2D plot of, basically if you look at acidity here's glucose and fructose, those are correlated, right? They're very similar sugars. And then some of these other ones as well, it's important. Now, the big deal about tensor networks is tensor networks have been around for a while, and it's really important to know that, especially this year and later last year, and probably even before that too, is there was a survey out in the middle of the year on tensor networks, and it goes over, and I'll show you the chart on that too, as far as everybody's research. But it's like the practical solution to high dimensional data. It has the capabilities of simulating all these different types of quantum circuits, which also could, do approximations on their own with circuit partitioning, and potentially with dequantized algorithms, improving not only machine learning, but other types of tensor networks and those types of things. But the main thing with quantum-inspired machine learning 2.0, this efficient way of doing machine learning on classical hardware, is basically not only do you typically, there's many applications to get potential better loss accuracy, but the key benefit that I'm seeing is that, especially in medical, is people complain that it's not explainable enough, not interpretable enough. And if you have a neural network that tends to be more expressive, that's inherently less interpretable. So they actually take, part tensor network, part neural network, and this is like, in big studies across the coast. So we see here, but those are the buzzwords. I think moving forward is interpretability, transparency, explainability, and it's tied with, and you'll see multiverse computing, basically using a tensor network, which is very similar to what I've done with the matrix product operator to reduce the model to like 30% of its, the LLM or the generative model down to a small fraction of its size. So you see, it's just got a broad range of applications. It started off as condensed matter physics, but has since, because of all this activity with, thought to be benefit of certain quantum circuits and systems, it's just being run on tensor networks, very practically. And the key is it's called high dimension, low rank approximations, which means it came in as high dimension data, and now it's a lower dimension approximation of that original matrix, basically. And there's just benefits in neural networks. There's some benefits in tensor networks. And like I said, I see kind of the fastest growth with it, approaching it not directly with accuracy or loss, but more on the explainability side, as far as we got this result, or the doctors got this result, and then now we need to figure out how, right? So it's always the benefit, the more and more you could do it. So I just came off this huge quantum-inspired machine learning paper by Hoyne et al. This is another one. It's only 22 pages, but it shows you all the different tensorial neural networks is the term that they use for convolutional neural networks, recurrent neural networks, transformers, which are huge these days, graph neural networks, restricted Boltzmann's machines. So that's that's a big thing. It's called tensorizing. You're just take a layer that's slow and you just tensorize it with like an MPO or a matrix product operator. And then I've seen it myself as far as like basically 100 times better loss performance. And this is a model by Google Tensor Network. And then usually that speed, or approximately the same speed, but a lot better performance. So it's just a huge field that everybody's just been waiting on. And they say like, it works, it's efficient, but the big results are coming in this year. And you'll be familiar with this term, cursive dimensionality is very familiar. So like kind of like the first slides I showed you with all these pre-processing techniques and kind of like, things that you don't see are reported. All of that has to go on in order to reduce dimensions, to make it practical. And say like, if you have two things that are strongly correlated, you would either maybe take one or combine the two. So there's other things going on besides just the PCA, PLS, and then tensor networks as well. So they say exponential number of dimensions converted to polynomial complexity. Now, the thing I want to highlight here is basically Flatiron Institute, which is part of Simon's Institute. These researchers that also do the iTensor Julia framework, they found a way to not only get significantly faster, accuracy, precision, is they say it corresponds to an infinite number of qubits, meaning that the mathematical expressions are not tied to something that's that goes exponential in runtime, basically. And you'll see these things. Neural networks remain a promising approach to integrate with Tensor. We see that all the time. And they're known for being just lightweight. So I would say it's a lot of it's at this point, if you're heading towards rocket science, I would just take it more towards like the practical application of, using an MPO where it makes sense to compress a model to get better. I would do that instead of a fully connected layer, a dense layer in a neural network. Just use this matrix product operator in a demo, and then I, further improve it. And I check the adjustability or the compatibility or configurability of, taking it and chopping it in pieces. John, do you have a question?
Yeah, I do. It's sort of a two-part question. One, what are the heuristics you use for dimensionality reduction? Number one, and number two, how do you expose that reduction of dimensionality in the explainability context?
Yeah, so that's all I have to get towards. I mean, it's the same kind of approach with shaft values and moderating features. So say, for instance, like you're controlling or you're setting this at this specific case. So I don't think it's anything new on that regards as far as what common literature is to do explainability studies. It's just I haven't got to explainability quite yet.
Okay. Yeah, I mean, it's explainability has deep tentacles into architectural design, obviously. And so it's not really a layer you can add on unless I'm misunderstanding something that you have deeper insight into. So when you say you haven't gotten to explainability yet, it begs the issue of how do you design explainability in the context of dimensionality reduction?
That was my assumption that that's part of current studies. I think that would be something that's covered. And like I said, with this, it's probably less of adding layers and it's more substituting. So instead of doing like this specific, fully connected layer, dense layer, whatever, you just run tensor network in that specific part.
Okay, thanks.
Yeah. Yeah. So, basically there's just a whole host of different applications that people have wanted to use tensor networks before. And if you're heading in this direction, it's basically the matrix product state, which is one dimensional. If you can get it down to a matrix product state, it's preferred because it has the best algorithms. But a lot of times, if it's a really complex problem, you might have to use a PEPS or a tree tensor network, which don't have as good as algorithms, or say, that might be still developing. So that's the takeaway with that is if you watch these lectures, one of the leaders, Staudenmeier, it's M. Staudenmeier, and he works at Flatiron Institute. He also designs iTensors or iTensor networks. There's a bunch underneath that. He gave a discussion that I kind of featured on this, and I would call it, if you're not coming from tensor network background, a requirement, because it just covers so much stuff that you would encounter future, and it's only like an hour long, something like that. But yeah, it's Staudenmeier. If you type in tensor network, say, into YouTube, you should be able to find it. So these are the things that I've been collecting as far as like approaches. So we know this existed. I've done the first one, less neural network parameters for better performance, decreased model size I've done on a smaller scale, and other people on a bigger scale too. Better performance, I've seen that. And then, yeah, I think where the sweet spot is Multiverse actually put up a slide this week, and it was mostly just talking about loss and accuracy and speed and size and less parameters. But I think the real sweet spot, because there's like 6 or 7 other methods to compress models traditionally, without tensor networks, that I kind of see that maybe going back and forth. But yeah, transparency is kind of like that first step. explainability a little bit harder to get to. Controllability, I did a big study on that. Efficiency, speed, problem complexity, and high dimensionality. So I would, if you're just starting off with tensor networks, head towards Stoudemire's lecture. If you want the condensed view of that, I also did a seminar on that in recent weeks. So, you could do controllability studies, and I did this across parameters, hyperparameters, and inputs. So parameters would be something like I'm changing the number of layers, or I'm changing the matrix size of the tensor network. Hyperparameters, which is like batch size, epochs, learning rates, and inputs, which in my case, I just did the, changing the data set size. So the papers to kind of check with this is this neural tensor network. This is kind of like it's from the sounds of it, there was other 2022 papers that were kind of stuck in this wave function simulation kind of thing. And they basically said that they were able to convert or combine this tensor network and this neural network with the best of both worlds kind of stuff. So this is NSF, MIT, and Harvard researchers. And then tensor network systematically exploits classical advantage. And there's pretty much for every quantum supremacy or advantage paper, there's a tensor network that'll come and, kind of disprove it. And then it's also just infinitely more practical, lower cost, those types of things. So we see this, the one making the most headlines is Multiverse, this Llama 2.7 billion. It's a generative AI model, large language model, reduced it to 30% of its size, keeping 90% of its accuracy. And they said that it also is very controllable and more explainable than the previous method, which, I've seen other studies that don't use quantum inspired and they're getting, good reduction in size and accuracy. But I think the sweet spot is with the inherent, nature of controllability and explainability. So this is a set of studies that I performed, and this first one is a matrix product state demo. And this first one allows you to change the graph vertice. So I would just go, and you'll see here, this is a 4, 5 to 6, and then 7 and 8. So it's basically the more indices you put in, it's going to bog down the computer more. And this is kind of like a starting point, and just getting the demos to run can be challenging. So this next one extends it more. So 9, 10, 11, 12, 13. And this 13 in specific did take some time on a high RAM CPU, which is like a Google Colab thing. And then this one is actually just changing the link space. So I changed it. You'll see the 3s here to 4s to 5. And it's the same. It's just the space between the graphs is now changed, right? So it's a good little exercise on the way to, bigger things. And there's a Google Tensor Network demo that's actually this matrix product operator that I worked on for several weeks. And that's a good one to do, that you can just get, straight into lower loss and, a lot of times faster times too. Now, this next one is basically, this is, they're calling it a TFI model class, so this specific class representing transverse field icing model. And then you'll see the different changes in the length that I made from 10. And it was only, I could only change by a factor of 10. So 10 times 2 times, or 10 times 3, or 40 or 50. And in this case, it did not match the energy and the should be. And this was an important point that the author made to this specific demo, that this has to match. And it didn't. But in this next case, increasing the J interaction strength, actually decrease the energy, and the energy and the should be energy in these cases matched, which was good to see. So that this would be more desirable results, going from anywhere from 1.2, 1.4, all the way up to this 2.0. And then this last one with the G parameter, it actually didn't change anything, with H bonds, energy, or the should be energy. So it remained the same as the original demo. But these are the types of adjustments that you can make. And again, it takes a while to get into this. And I had to research a ton on iTensor and TenPy. Now, the good thing about iTensor, this is the group from Flatiron Institute that had this most recent paper, is in PRX Quantum. And this is Stoudemire. And again, definitely check out his lectures there too. And I actually found this out after I did my post. and it's the papers using their library. And this is probably the best way to start, because you can rule out a bunch of these and to see if people are actually working in your area. So I'll include the links up for these. There's at least 40 of the iTensors, and it's mostly Julia based. It's also C++ with just a tiny bit of Python. With the 10Pi, this is obviously Python based. They actually just hit version 1.0 this week, which is probably a huge success. And we see this reflected in literature with the results getting better, I believe. And, so 1.0 version is basically something that's more, addresses previous issues, back compatibility issues, and more a general product. So 10Pi. Now, between the two, it seems like maybe the iTensor is seeing more of the innovation and the papers, and just by watching their different seminars and interacting in different ways with iTensor, this seems like more maybe the cutting edge stuff. But the downside is like I said, mostly Julia, C++, and if you want to start compressing a model that's in PyTorch or TensorFlow, that's an issue, because this is in Julia as a direct route. That's the way it looks like right now. Whereas the 10Pi, probably a lot easier to work with other Python libraries. So I found this interesting quote. So this is David Donahoe at Stanford University's Department of Statistics. And this is actually going back to 2000, but it still applies today. We are now in a setting where many very important data analysis problems are high dimensional. Many of these high dimensional data analysis problems require new or different mathematics. Okay. And that was like the dawn of like deep learning. We didn't get TensorFlow and PyTorch, publicly available until like 2015, but the hardware was getting good enough that you could consider these AlexNet models, or probably a LaCoon, these types of things. And it says the central issue is the curse of dimensionality, which has ubiquitous effects throughout the sciences. So, and that's what I showed, is basically PCA, PLS, and now tensor networks addressing that in their own specific ways. So, that's the big takeaway here. Now, are there any questions regarding any of the slides? And, if anybody needs additional breakdown with this, because it's like, I came from different angles with this, and, the whole quantum inspired stuff with the 1.0 software, which would be your average like Penny Lane or Qiskit demo, was aimed more towards running on a quantum computer in the future. But now with tensor networks and different approximative techniques and circuits and dequantized algorithms too, is that, especially with sensitive data, is we can just run this on classical hardware. So, figure the short wins right now will be simple incorporations of tensor networks into neural networks, compressions and like. And then the larger wins will come with these big dimension, like how we described before, with N being the number of patients, and then P being the number of dimensions, and especially, dealing with P in a lot better tensor network ways. So any questions or comments? So it's a field, like I said, it's been in the works for some years, and the whole stuff with quantum computers and the intrigue to try to run them on quantum hardware has further accelerated tensor networks, just because that's how everybody does experiments anyways these days, is on like CPUs and GPUs. So like I said, so if you have any questions, feel free to put in the chat. And, as far as what's on the horizon now, it's definitely the iTensor software appears to be, there's many other repositories under iTensor on GitHub. They're not at 1.0 yet. And I would stay away from the folders that say test, because that's usually means that they're testing, not you. But head towards the examples. I found that specific, the graphs and the vertices, that specific product there. And if you might have to bootstrap too. If you use Python, bootstrap Julia, and then you're kind of on your way. And they both have discussion forums, iTensor and 10 pi as well. So it's definitely the type of field, like, if you were looking for excitement and breakthroughs, like I said, with tensor networks, it was condensed matter physics for the longest time. And, basically figuring out things. The team at Flatiron Institute that I refer to, they use a technique called belief propagation. And that was kind of their claim to fame, to get to run a quantum circuit 127 qubits faster, more precise and more accurate, and scaling up to an infinite number of qubits is what they said. So it's exciting stuff. But yeah, Flatiron Institute is basically the I believe it's the physics branch of, I don't know if it's just physics or quantum physics, of Simon's Institute. Now, Simon's Institute is known for having these awesome lectures where people come in, they're the leaders of the field. This is in Berkeley, I believe. And we saw one from Yuan Tang of the dequantized algorithms. And I also saw other, at least one other tensor network seminar there at Berkeley, or in Berkeley at Simon's Institute. So yeah, Flatiron and Berkeley are kind of connected. And I think the big thing will just be whoever gets the next awesome results. These icing models are thought to be very beneficial. And I think that was the experiment, the 127 qubit that, that they said did very well. Questions?
Hey, Kevin.
Hey, Ron.
When you say 127 qubits, are you talking about the IBM Eagle processor or a simulation of some sort?
No, it's against, so it's the 127 hex qubit on the Eagle. And then
On the Eagle, yeah.
Yeah. So that was thought to be, because the previous experiments with quantum supremacy in 53 qubits, the tensor networks kind of took care of. And then this one, like I said, was much faster, more precision, accuracy, and scalable too.
Okay. And I know in the past you talked about implementing qubit gate algorithms by grouping them into parallel bunches, so to speak. Where
Yeah.
you'd have like blocks of 8 qubits. Have you actually tried moving that over onto the Eagle and see if those blocks of independent qubits, which aren't connected to each other, but are connected within themselves, whether you get any, what kind of performance you get doing that?
No, I mean, we all know how much noise and decoherence, and then on the algorithm basis on its own with dequantized algorithms, I disprove quantum computing for QML. So there's other potential use cases for quantum computers, but I'm primarily focusing in AI. And basically, if the technologies, because AI is moving at such a high pace, if the technology does not work today and is not improving AI with speed or performance, I believe that it's at serious risk of not being used in the future for AI.
Yeah, you certainly don't want live quantum machines involved in any of your training or inference cycles. It just won't be any fun. But I was more interested in just wondering if an experiment could extend the usefulness of like the 127-bit Eagle.
Well,
if you put blocks of eight qubit networks on there and they're not connected to each other, you should be able to keep your circuit depth pretty low, right?
Yeah, I mean, in theory, yes, these are as opposed to entangled and CNOTs, but I mean, the bigger issue, because I'm not really focusing on anything beyond just quantum inspired machine learning for AI to improve AI. And the kind of the silver lining would have been if you could get quantum data to run on a quantum computer, but the quantum sensors today aren't even producing quantum data, which means that there's very little insight into the future with quantum computers, and especially with Kimmel and AI. So these are probably valid experiments, but it's just not something I would get into because if you see like in 5 years, they're saying like no more coders, like on a traditional sense. And in my opinion is you have to know machine learning, and that's done by coding, but we're going to be interacting with AI and supercomputers more on a prompt basis as opposed to hardcore coding. But that's the dominating feature right there. And like I said, I think in my opinion, as of today, if the technology, to be used for AI is not working today and can't improve AI today, then it's going to be a very hard sell. And I don't see it's working. So, that's why I switched to quantum inspired machine learning, and especially this 2.0 software, is because it's working and the results are much better. And there's all this other, intrigue in using it for high dimensional cases beyond just quantum circuits. So
Yeah, I mean, I don't disagree with that. Gate-based quantum machines are still in their infancy. I mean, there's the annealers out there are actually making money with business problems, especially in the optimization space. I'm actually doing that now. You had mentioned something about some data sets with specific feature sets. Were you referring to data sets that you're testing with that have a large number of features?
yeah, so that would be like for explainability studies, like John had asked. So this is more like for SHAP values, and it's more a universal thing. I don't think it's anything in specific with incorporating a tensor network. It's more or less like if you change these features up front, and then for one study, and then the next study is you remove a feature, and the next study is that's how it looks like to do that. And again, the multiverse computing, they said that they got controllability and explainability with their model compression with their tensor network. And this is like on a jumbo screen now, that specific slide. Actually, that slide is more for performance, but in the paper, they did say, controllability, much greater controllability and explainability.
Yeah, I don't think anybody can explain how generative AI works, but it seems like pure magic. Um, the reason I was asking about features is I'm on the lookout for a data set with a large number of features. Doesn't have to have a lot of records, but a large number of features that support a classification problem of some sort. And another area in quantum and machine learning that's becoming pretty hot is again not involving the quantum computer in the training or the inference cycle, but using quantum optimization up front during the preparation phase. I've done some experiments where I reduce a data set which has about 300 features down to 80 features, and people are willing to pay for that, because if you go from 300 to 80 features, just you can imagine how much shorter your training cycles will be.
Yeah, it's going to be a hard sell, especially anything in medical. When you're talking about anything that has noise or decoherence.
No, I'm not talking about being in the machine in the training cycle. I'm talking about doing feature selection on a data set to figure out which features don't matter.
Yeah,
It's an optimization step.
maybe
And
for some people, but I really can't have any association with anything that would have noise and affect like a sensitive data at any
there's
point.
no noise issue when you're dealing with annealers. It's actually outperforms the machine learning probability. And again, you're only doing this once up front. You're doing it to prepare your machine learning pipeline. You're not using it inside of the pipeline. So
Yeah, I understand. Any other questions? I see Samuel, you had a couple questions here. Yeah, so most of the research that's been done so far with quantum inspired machine learning was with 1.0 software. Now, I would define 1.0 software as anything that's not optimized for classical computers, which it's running on. So the more, there's Alzheimer's research, there's brain tumor research, there's these type of things that exist, but everything's the same. And I've run these, ad nauseum, going up to like 44 classes with like 4,400 images. It's just really slow because you're trying to do it in the way that a quantum computer would do it, and it's not efficient to do that on classical computers. So like what other companies do is they take a small portion of the Hilbert space, and then you're working with that model correlation space instead of trying to do it like you're taking the best of quantum and then doing it efficiently on classical hardware. So I haven't seen anything kind of drop on the more efficient stuff with tensor networks or circuit partition circuits that are efficient to run, or dequantized algorithms for that. So, and I would stay away from all of the other research because it's just way too slow. And you have to ask yourself, like, is this significantly better results for the amount of time that I'm spending? And you might get a better accuracy on an epoch basis if you run 20 and 20 on the classical, but on a time basis, you're going to have, you could probably catch up on that performance by running the classical model just longer. And that's the thing, I had to separate between quantum inspired machine learning 1.0 and 2.0 is because most people associate it with slow, and it works. It's just like the performance is not there. So yeah, I would head towards the most theoretical papers that are highest performance. Usually the medical papers at this point for quantum inspired will probably still be using the old software. But if you search for dequantized algorithms or tensor networks or circuit cutting with some of these circuits, that seems to be the route to go. So one other thing from Samuel, so with AI programming basic codes, even at the level of quantum algorithms may no longer require human interference. Yeah. So that's why I'm saying is it's kind of like a breaking point. Like Jensen Huang went on a couple of weeks ago in Dubai and basically said, don't get a computer science degree because in 5 years, the computers will code on their own. So you have to be the one that's impacting AI in new and different ways and know how AI works by running your own machine learning code. But yeah, and I keep seeing it in my feeds, and it's reflected in other people. The AI will speak the human language, and it will know every type of programming language that's out there. That's the thought. And this is like OpenAI, NVIDIA, and others too. Yeah, so everything is going to change. And they all say like we'll become prompters, so for AI. And obviously anything that can make the software run faster to implement it into AI and to become the subject matter experts with that too. So the GTC, I think for NVIDIA touched on it a little bit as the grand scope of AI with multiple agents talking to each other just like humans would, and they all do their own kind of tasks called NIMS, NIMS, and that's associated with biology or medical is what I took from that.
Yeah, could I ask a sort of a multi-part question? So it's interesting because some of the multi-agent conversations that are being produced, one of the earliest learnings was they had to cut them off or they would talk incessantly.
Yeah.
And so I think that once we figure out how to create the social networks of multiple agents in a conversation, tackling a problem from different perspectives, we're actually going to replicate the social architecture of humanity in silico. And so the question or the assertion was made earlier that nobody really understands how generative AI works. And I have a hypothesis. And I was an evolutionary biologist before I got into tech. And so this is sort of based on an evolutionary biology lens. But it strikes me that the way we craft our language and communicate with each other is we don't go word by word. We go thought by thought, meme by meme, phrase by phrase, concept by concept, and a concept can be embedded in a phrase, a sentence, a paragraph. And why is it that we wouldn't assume that the in silico representation of LLMs isn't mimicking the biologic carbon-based approach to taking large data sets through life experience and transferring that into larger components than letters and words. And why isn't it sort of a default assumption that that is the way that LLMs formally operate? I'm just, curious if anybody else has arrived at that null hypothesis, or whether there's any experimental evidence that that might be the case.
Yeah, I mean, it's something. I go to other AI talks to pick up a lot of this, and other advanced ML talks, and it's, a lot of this, if you're not familiar, it's like generalized artificial intelligence. Now, if you use AI, like how we mostly use tensor networks today, that's for specific simple AI tasks. And I don't know, as far as like, will it be exactly the same as human society, as what's going on in the computers? But I think we'll get a pretty good idea in the next, I don't know, at least a year, as far as like what the jobs are going to be like, because it's basically a few of these huge corporations that are controlling all of this. And I still think, in talking to others too, they say PhDs and postdocs, yes, we need you, but like the entry level programmers, not really. And just things will shift. So it'll be interesting, but there's lots of things involved, and some companies aren't in favor of this, because if you have robotics and then, if the robot is reprogrammed in ways that you don't want it, and now it's acting in it's there in its own way. So, but I think the thing, especially with medical, is it's embracing a lot of this technology. Like I think NIH is not funding generative AI at the moment, but like Stanford Medicine, you'll see generative AI, and they're basically, a lot of these companies are within shouting distances of each other in the Bay Area. So we're seeing this with an ex-FDA commissioner, Scott Gottlieb, saying, LLMs are coming. It's not going to be trained on the entirety of the internet like ChatGPT, but it's going to be more focused in, specific medical data sets and, things that really apply. And actually, I think there was actually a Stanford announcement this week to, it's more like you call in and an AI bot answers it, and then maybe more triage, not in a direct medical way with these huge models quite yet, but kind of like getting to that point.
Those medical models are here, and they're going full blast. Google's MedML is scary good. I've been involved with that for the last 2 weeks, and there's all sorts of scenarios where they can plug that in. They can have it look at a patient encounter and do all the paperwork on it. They can have it look at a particular diagnostic result and make assessments. Those things are there. And they don't need to be trained on the entire internet, is true. They just need to be trained on a medical dictionary and every scrap of medical data they can get. I mean, these things are they've been trained on everything that you can find on the website over at Medicare's the Center for Medicare Services. Every document that's over there, whether it be a guidance or a specification or a rule or whatever, it's fed into the thing. I mean, it can actually tell you in the middle of an encounter whether you've done enough to justify a particular level of encounter code and get paid a higher price for it. I mean, it's actually, again, it's scary how good it's gotten. So that's happening. And if Google's doing it, everybody else is doing it too.
Yeah.
Open AI. I've also been working with Open AI's Gen 4. It's so scary. A lot of big corporations won't let their people have access to it in its capability and stuff. But this concept, it's just a tool. I still have never seen anything that would make me think that it's conscious or it actually understands anything that I'm trying to get it to do. It's just a tool that has this vast array of capability to merge data together. You could easily trip it up. It makes mistakes. It hallucinates. Um, you know, it's very addictive. I warn anybody who signs up for G4 and pays the price that you could get addicted to it. It's like, but it can, and you can get a good laugh out of it. Its mistakes can sometimes be incredibly humorous. But we ask it to do simple things like translate computer language from one to another. That sort of stuff it does. You have no way of measuring the precision, however. But all of these tools are, they're being filed as co-pilots. And they're getting, they are getting bigger and wider, and they're adding more bits to the, to how, I forget the attention span is, so to speak. They have another word for it. They'll get better as time goes on, but to actually think that the transformers involved in it are replicating human neural nets, I'm not so sure about that, but
Yeah, it'll probably be
crazy.
a different way. Yeah, I mean, a lot of it, like FDA approval stuff, is they used to just be AI, ML locked algorithms, and some of them still are, like Apple's, the wrist software with the irregular heartbeat
Yeah.
notification, that's locked. But now they allow, like, so over a course of so much time, you can retrain on different data, or if it's shown to have bias, address the bias and fix it. It's called algorithm change control policy and SPS. But yeah, I see it, especially with the medical stuff being a lot more controlled. And even if you go through all these AI ML approvals, you'll see that it's a progression as far as, like, you could have a brand new approval, but it's not giving much power on the end of, like, on a prediction, like it still has to be approved by other clinical factors. So yeah, I see it just being a little bit slower, or maybe a lot slower for medical as far as like this super cutting edge stuff. But so in October last year, FDA said there's no LLMs, in this whatever, which was kind of strange because usually you don't see a specific technology called out before all the other ones. So a lot of these probably coming through in a more kind of customer or patient interaction, as opposed to, like, we came up with this prediction and this is the definite thing, and the doctors don't have as much control. So it'll always be like that. I think I don't in my head know exactly what humans will be doing in medical AI in 5 years. I still need to collect more information, but I do know that the pace of AI is just moving so fast. And one of my colleagues says the moment that you pick a model and you click play to deploy, it's already out of date. That's just how fast it is. So,
So the thing is, with medical, there's a lot you can do, and you don't need approval as long as you're not in the diagnostic pipeline. Doctors can use it to do research. I mean, they still have to take responsibility as being the final authority. They can use it to do a next step in a patient a patient's path, but the software itself cannot be responsible for making the diagnostic or making the plan, but it can still be used as a tool.
Yeah.
So,
Yeah.
by the way, you'd mentioned NVIDIA, Jensen and NVIDIA. Their GTC 2024 is wrapping up this week. I highly recommend everybody jump on the NVIDIA website. Jensen's keynote, which happened last Sunday, is up there. I warn you, it's 2 hours long, but it's amazing where they're going, and they're going to. He introduces their Blackwell platform.
Yeah, I saw that.
It's crazy. They have a exaflop of performance in a 19-inch rack. That's a billion floating point operations per second.
Yeah, pretty
That's
awesome
crazy.
stuff. Now,
Yeah.
anybody that we haven't heard from, either Samuel or Mo? And then John, if you have anything else. And I definitely appreciate everybody coming on. So this was event. Did you have?
Sorry. Yeah, I thought I was off mute. Sorry. So I have a question for Ron. Is the Google Med LLM operating in a RAG architecture? Is that how they're doing it, or is it a different approach?
I can't say for sure, although that term has come up in the sessions I've been in. Unfortunately, as far as I know, this is not a product that is directly available to the public.
Right, right.
So we're getting special access because of one of my clients, but it's scary how
Yeah.
good it is. But again, it's just a matter of enough bits to put the data in the right order, and that'll be here faster than anybody knows. So.
Yeah, and to your observation that, it cannot be autonomous in making diagnoses or therapeutic recommendations. I actually co-authored a paper on that very top. I'm a recovering physician, and I co-authored a paper on exactly that point. And it's really use case specific. So there are certain situations like radiologic imaging. The machine is so much superior to a human that we're at risk of having humans reading and reviewing the AI output and having not a clue how to override it. And there was actually a paper published in the Journal of American Medical Association recently by 4 pathologists in 4 different countries, saying that the scary thing is that it's so good at image interpretation because it can operate off of millions and millions of images that no human could ever analyze in the kind of detail that every one of those images is analyzed by image processing, that we may be at risk. This is a kind of a fascinating conundrum. We may be at risk of losing the very heuristic skills of the pathologist looking at slides and integrating that in a multimodal context with the clinical information, that will have very, very few people who are actually competent to overread the AI output in the imaging space. It's and to the point that Kevin was making about, we don't know where we'll be in 5 years. It's hard enough to predict where we're going to be in 5 months. As you say, by the time you're deploying one of these solution sets, it's already obsolete. It really does raise issues with FDA certification, something I've been involved with. That's the context of the paper I authored in that space. And it raises serious issues about the cycle time disparity between the pace of evolution of AI and the capacity of regulatory agencies, which are fundamentally designed to be very slow, to be very cautious, to be very certain. And we're basically have a runaway train in terms of having a regulatory framework, environment, test bed, protocols, heuristics for managing what I've coined a term, the diadarity of the human in the loop. The human is being squeezed out of the loop both by the pace of technology as well as the asynchrony of the cycle time of the regulatory processes. So it's for the time being, I think most people in the medical space are looking at it as one additional input to the human clinician. But I don't know that that's going to last very long, because already in the imaging space, the humans are dwarfed by the machine.
Yeah, I mean, I think new techniques will come. If you're talking about radiomics and just more and more authority being given to computers to look at all these thousands or millions of images, so I think that's still in play. Any other last questions or comments?
Good to see you again, Kevin.
Yeah, so everybody, great discussion. Hope to see you guys next week. This is Event Seminar 127, Tensor Networks, PCA and PLS for high dimensional data sets. Have a good rest of the night and have a productive rest of the week, everybody. Take care.